Welcome back, Chemistry 30. This is EQ1.1, concept of equilibrium, where we look at what is meant by chemical equilibrium. So to be in equilibrium is to be in a state of balance. So you could imagine a tug of war, for example, if we had 4 people on this side, 4 people on this side, and if they're all combined equal strength, of course there'd be equal pulling in each direction, and it wouldn't move. We would say that would be a static equilibrium. And static refers to at rest. So things are not moving. There's a state of equilibrium. It's a static equilibrium. If we look in terms of what we're going to be looking at in chemistry, though, chemistry deals with dynamic equilibriums or equilibria. And the word dynamic implies moving. So we have things moving. So equilibrium can be dynamic, as illustrated below, which shows a bridge between 2 cities. So if you were to imagine if we had city number 1, let's say there's 100,000 people. Okay, and let's say we have city number 2, and we have, I don't know, 500,000 people. And here we have a bridge in between those 2 cities. So people from city number 1 can go to city number 2 and vice versa. Okay? So if we look at, we could have, if you look at this bridge here, there's headlights showing cars going one way, cars going the opposite way. If we have, for every 10 people we have moving in this direction, we could have 10 people moving in the opposite direction. So if you look down below here, the rate at which cars leave one city equals the rate at which they enter the other city. The 2 opposing processes are in balance. And the net number of cars is constant. That's a key word to note. I'm going to circle it, and I'm going to say here, constant and constant. So for example, city number 1 will stay constant at 100,000 people, because for every 10 or 100 that go in this direction, to the 10 or 100 go in this direction. So we maintain constant. So chemical equilibrium occurs when the forward and reverse reaction proceed at the same rate. That's another key word to point out. So we could go maybe draw something like this down here. Exiting and entering, we could say, oops, equal rate. Okay, so have something like that. So if I have 10 people leaving, 10 people are returning. It is an equal rate. Yes, so equal rate and exiting. So the two key things here is that the amount of people in each city is constant due to an equal rate here. The amount of people leaving is equal to the amount of people returning, which causes these to remain constant, unchanging. They don't have to be the same. Like here we have 100,000 people, here we have 500,000 people. So we don't have to have the cities being the same size, but to be equilibrium, a dynamic equilibrium, they have to remain constant, unchanging, because of the equal rates in between. All right? All right, so if we apply that to chemistry now, we could have a scenario in which we have a reaction. Let's see here. So if I have N2O4, producing NO2, of course I have to balance it out, it looks like that. So I could have an equal rate with that too. N2O4 breaking down to give NO2, and that reversing to give this. So notice that these will be reversible reactions. So this quite often happens with gases, for example. Of course, it doesn't occur with the frying egg. You can't get the original egg back, but gases, for example, can make one gas or two gases, then go back and form this. So that would be a reversible reaction as well. So if I was to have a sealed container and place these gases in there, eventually what would happen is that they would reach equilibrium. In a closed system, things always achieve equilibrium. So if I look at this, this is a rate. And for rate, you can think about how fast things are happening, how fast reactants are going to products, and how fast reactants or products are going back into reactants. And eventually, an equilibrium is reached. So if I look at the forward reaction, for example, or the forward reaction would be the amount of N2O4 getting used up. So the rate at which it's forming products is slowing down. The rate at which NO2 is going back and forming this is speeding up until eventually they get equal rates. And that would be signified by a plateau area that is equal for both. So at equilibrium, the forward and reverse reactions are proceeding at the same rate. So that is always achieved during a chemical equilibrium in a closed system. And of course, the reaction has to be reversible. If I look at the concentrations of each, how much there is, how much reactant and product there is, I can get an idea of what's going on there. So again, this is the reaction of N2O4 forming 2NO. So how much there is. So we have, if I just simply place this initially, if I only had that initially, and I didn't have any of NO in the flask, of course my N2O4 would start off at a large amount. So I'd have some and I'd have none of the NO. But as the reaction happens, as N2O4 molecules start to break down, there's less and less and less and less N2O4 molecules, and there's more NO molecules forming. Now notice they don't have to be equal. Just like in that city example, we don't have to have equal numbers and equal population. Similarly here, we don't have to have the same amount of reactant and product. Again, what happens here is a flat line though. N2O4 gets used up until there's a constant amount left over. NO2 gets produced until there's a constant amount. So this is signified by constant concentrations. All right, so constant concentrations. So the amount is constant, unchanging. Doesn't have to be equal, has to be constant. Okay, so that's a key thing to note. The idea between equal versus constant. The rates are equal. At equilibrium, the amount of reactant forming product and the amount of product forming reactant is equal, just like the bridge in the city example. And then the amount of reactant and product that exists is like the two city populations, constant. So depicting equilibrium, since in a system at equilibrium both forward and reverse reactions are happening, so both forward and reverse are happening, we write it, as you can see up above here, I wrote two arrows. If it's reversible, reactants form products, products form reactants. We usually signify that by a double half arrow. So you can see kind of a half arrowhead going to the right, half arrowhead going to the left. That's common practice in terms of showing a reaction that's at equilibrium. Once equilibrium is established, the concentrations of N2O4 and NO2 are no longer changing. However, the fact that the composition remains constant does not mean that it's not doing anything, because we have to realize that it is dynamic, constant movement. So let's highlight that. Constant movement. So we will have N2O4 making this and NO making N2O4, constantly moving. So we can say N2O4 is always converting to NO2, and some NO2 is constantly converting to that. So it's a reaction that's continuously happening. To our naked eye, it appears that nothing's changing, but in fact, things are moving, but the net effect is a constant amount. Okay? So key things here. Key things that we learned from equilibrium here. For equilibrium to occur, neither reactants or products can escape. So it has to be a closed system. Okay. Also needs to be a reversible reaction. So you have to have the ability to go in reverse, go from products to reactants. At equilibrium, the concentrations of reactant and product, so the amount that we have is unchanging, constant. Again, it doesn't have to be equal, just like the city example. And in equilibrium, the forward and reverse rates, so the speed or how fast they're going, that is the part that's equal. All right, so that's an introduction to chemical equilibrium, dynamic equilibrium. You should be able to do the EQ 1.1 assignment now. All right, we'll see you again.